Hello, everyone. My name is Yang Liu. I'm a senior lecturer in Exeter University. And today I'm going to talk about one of my research projects on this self-propelled capsule for small bowel endoscopy. And I'm probably starting from different aspect from the first session. And I will focus on how to use the mathematical tool to help us on optimization and control of our robot. So I will focus on quite a bit on this mathematics. So in my talk, so initially I will introduce the background and motivation of the project, and then the working principle of our design, and then I will introduce the mesoscale prototype and followed by millimeter scale prototype. So in both of the prototypes, I'm going to show you the mathematical model and comparison between numerical and experimental studies. And finally, we will have some finite element and experimental investigations. So at the end, I'm going to give you the concluding remarks of this research. So motivations. So capsule endoscopy is the primary modality for examining small intestine. And the burden of this gastrointestinal disease is quite heavy in the UK and also in the world. So it has been doubled in the demand has doubled in the past 5 years, and also it's growing every year. So what currently capsule endoscope do at the moment? So they imply miniaturized the camera in this capsule, and then the patient will swallow that. Because the capsule is passive, so it will be driven by the peristalsis of the patient gastrointestinal tract. So this makes this capsule has a number of limitations. As you can see, this figure, and it shows the capsule is stuck somewhere in the GI tract. So the clinician need to take a surgery and remove the capsule. So another disadvantage of the capsule is sometimes it could move very fast, so the camera cannot capture the symptoms in the GI tract because of the peristalsis, because it's driven by peristalsis, and so the speed cannot be controlled. So there are quite a few research groups, and they are working towards developing different kind of controlled capsule endoscope. So they use, for example, this one, they use propellers, and this one using legs. They want to control the motion of the capsule in the GI tract, so the clinician can carry out a careful examination on the small intestine. So our design is a bit different from this works. So, but our working principle is quite simple. So we base on the Newton's third law. So if we look at this two mass system, we have a smaller mass and a larger mass. So if we generate a force between this, we have force and a reaction force. If this force is a symmetric force, and then the whole system under the friction will oscillate at its original position. But if we make this force asymmetric, like this, and then we can control the direction of the system by controlling the force profile of this excitation. So imagine if we put this small mass inside of this bigger mass as a capsule, and then we can control the force profile. Then we can control the motion of this capsule and control its direction either forward or backward. So this is the main principle of our design. So in order to verify this principle, we developed this mesoscale prototype. So it's a bit large because it's about 56.9 millimeter in length and 19.4 millimeter in diameter. The reason we developed this large one because we want to try to integrate a number of sensors. For example, accelerometer, we integrate that into the inner shaft, which is the inner mass. And we also put a displacement sensor on the capsule to measure the displacement of the capsule. And then we employ this solenoid, and we apply the current, and we can control the linear motion of the shaft. So in order to introduce the asymmetric force, so we bring the two constraints. So there is a one forward constraint and backward constraint. So once this shaft is linearly excited by the coil, it may contact with the constraint, forward constraint or backward constraint. So impact may happen. By using this impact, we can drive the whole system moving forward or backward. So this in this talk, I'm going to introduce two of the cases we carry out for our experiment. So the first case, we run the system on aluminum bench, and the second case, we use a synthetic small intestine, and we carry out the experiment. So as you can see, this is the experimental rig, and we can see here is the shaft connecting with the accelerometer, so we can measure the acceleration of the inner mass, and then we have the displacement sensor to measure the displacement of the capsule. And so this is and then we can record these signals and analyze for the dynamics. In order to understand the dynamics of the prototype, we developed this mathematical model. If you look at this picture, we have an inner mass, which is the shaft of the robot, and it's connected by a linear spring K and damper C with the capsule. And K1 is the front constraint, and K2 is the backward constraint. And then the whole system is under column friction. And so in this system, we excite the inner mass using a square wave excitation. So we also can use harmonic excitation, and we can apply both of the excitation. But today I'm going to focus on this square wave excitation. If you look at this square wave curve, we can see there are three key control parameters we are going to use. So PD is the amplitude of this excitation, and T is the time duration. In other words, it's the excitation frequency. And D is the duty cycle, which is the ratio of time on, duration on, divided by the whole duration of the excitation. So we are going to change these three control parameters to understand the different dynamics of the system. And on the right corner, we have the equations of motion for the prototype. For the first equation, it's related to the inner mass, and it's under this square wave excitation, and the Fi is the interactive force between the inner mass and the capsule. And then the second equation is related to the motion of the capsule, and it has a column friction and interactive force from the inner mass. So in order to use our mathematical tool, which we called as path following techniques. So basically, we follow a desired trajectory of the system, and then we check when the system dynamics will change. Maybe a very significant change. We call that bifurcation. And so we divide the system trajectory into these 18 modes, operation modes. So this corresponds to like no contact with the constraint, and contact with the front constraint, or contact with the backward constraint, or excitation or no excitation. So this covers all the operation regimes for the system. And if you look at this picture, this is from the simulation of the model, and you can see different colors of this trajectory, which is the displacement of the capsule. And you can see this different color represent different modes of this mathematical model. And there are two key parameters, solution measures we are going to use for optimize our design. So one is the average speed of the capsule. So we try to control the speed. In this case, we try to the highest speed of the capsule. Another one is the maximum propulsive force generated on the capsule. We want to minimize this because we don't want like actual force acting on the patient's intestines. So we want to minimize this maximum force, but we want to keep the speed of the capsule as high as possible. So this is the first case. We carry out the experiment on an aluminum bench, and we play with these three key control parameters: frequency, amplitude, and duty cycle of the excitation. As you can see, when we increase these three parameters, the simulation and the experiment are fairly consistent. And these two examples are the time series of this comparison. We can see the square wave excitation and also the acceleration of the shaft. And in this case, we only can see the backward impact, and there's no forward impact. So the capsule moving backwards in this case. But when we change the excitation duty cycle, and then we observe the forward impact and also backward impact. And in this case, forward impact is much higher than the backward impact. So the whole system moving forward in this case. One interesting observation is here we observe a bistable state for the system, and we further explore this bistable states. What we found is there are two states coexist. So if you look at this phase trajectory of the system, and then this is the forward impact constraint, and this is the backward constraint, we can see the shaft has a forward and backward constraint impact, and then the system moving forward. And in this case, which is coexisting with this state, it has no impact at all, and then the capsule is stationary. And so what we want here is we want to avoid this bistability in the system. So we employ this continuation technique or path following technique. So we try to, for example, we can follow up this trajectory of the system and detect when the bifurcation will occur. So we can avoid this region. So by doing this, we carry out a two-parameter study. So which two parameters? So one is the excitation duration, and another one is the duty cycle. So in this case, we can identify a region. In this gray region, this bistability exists. So in this region, we are not sure if the system is moving forward or stationary. So it's when we choose control parameters for the experiment, we can choose this area for forward progression or this area for stationary state condition. So by using this, we can provide control parameters for the experiment for the robot. And the second case, we running that robot on a synthetic small intestine, and we also play these three key control parameters, and we can see as we increase that is also consistent with the experiment. And what we observe here, very interesting bifurcation point is when we increase the duty cycle of the system from 0.2 to 0.5 somewhere here, and then we observe a bifurcation here. The system initially the capsule moving backwards with period 1 backward motion. And then once we increase the duty cycle, the system becomes a period 2 forward motion. So the direction of the capsule changes. If we further increase the duty cycle, the capsule moving in period 1 forward motion. So this can give us an idea about how to control the direction of the capsule by changing the duty cycle. And we can follow by using the path following technique, we can find a boundary for this bifurcation. So we can choose parameter whether we want forward progression or backward progression. So by doing this, we're trying to track this bifurcation, which is called period doubling bifurcation. And so in this case, we figure out this two parameter space. We can identify a boundary like this line. So in this region, if we choose parameter here, and the system will moving forward. And if we choose the parameter on this region, the capsule moving backward. So this gives us a control method to adjust our control parameters to control the direction of the capsule. And then we move to the millimeter scale prototype. Once we are happy with the mesoscale, the size of this millimeter scale is 26 millimeter in length and 11 millimeter in diameter. And it is a standard size capsule used in the hospital at the moment for the capsule endoscope. And then in this design, we employ a T-shaped magnets, permanent magnets, and we decide to put our coil external like this. So we use external coil to drive the capsule, and it can give higher, much powerful driving force, and also it will not cause any heating problem. So we use the same idea. We put this permanent magnets through a linear bearing here and connect the capsule through a helical spring, and then we put two constraints, the primary constraint and the secondary constraint. So once the permanent magnet is excited by the coils, and it will impact with the front primary constraint and the secondary constraint. And in this case, we use a video camera to monitor the progression of the capsule, and also we use a square wave for excitation. Of course, we have done the calibration of the electromagnetic force generated by the coil, and what we found is we have the analytical model, simulation, and experiment, which fit very well. As you can see, when the distance between the coil and the magnets is getting further, and the force getting smaller and smaller. And we are operating our capsule in this region, so the distance around this region, so it could give us a good performance. And here is the experimental and the numerical result comparison. And we carry out experimental result by changing the excitation duration, or in other words, is the frequency of the excitation. And what we found here is green dots here are the experiment, and the red line is the experimental average result. And then the blue line, blue dots are the simulation result. As we can see, the trends are fairly consistent, and the highest speed, which is this is the average speed here, is around this 30 to 40 milliseconds. And here is the time history comparison between simulation and the experiment. We can observe both forward progression of the capsule and also backward progression of the capsule. As you can see, we need to drive the capsule on the small intestine smoothly, and we don't want actual impact force. And because when we need it, we can introduce the impact force, but we don't want it. When we don't want it, what we did here is we did optimization. So we try to optimize the speed of the capsule, but also we minimize the maximum force on the capsule. So in this case, we can figure out, we can find a good optimized parameter, excitation frequency or excitation duration, and the system could have the same progression speed, But in this case, you can see there is the impact force generated on the capsule, and this is something we don't want. And then in this case, we have no impact actuation at all. So this is our preferred condition. So this we can use this to optimize the propulsive force on the capsule. to follow this, so now we follow this trajectory, we can further figure out in this 2-parameter space, we can figure out the boundary, and it shows in this region there is no impact for the trajectory, but in this region there is an impact. As you can see, this is the back impact of between the inner mass and the capsule. So we try to avoid this region, and we choose the parameter in this no impact region. And we further carry out the experimental and numerical comparison to justify this boundary. And what we found is the green triangle are the experimental result for impact solutions, and then the red squares are the no impact solutions. And it gives so in this case it gives our capsule a smooth actuation, so the capsule will not generate like impulsive or quite large force acting on the intestine. So so here we try to understand the maximum magnification factors from our design. So what we did here, we in this video we implement our mechanism into a commercialized capsule. As you can see, it can drive on the small intestine very well and very smoothly. And what we found is the best magnification factors will be around 30 Hertz of our design, and it can has the maximum magnification in this case. We also, another challenging issue is when we consider the internal structure of the small intestine, we can see there are quite a few, in the small intestine we have the circular force, which will provide quite large resistant force for the capsule crossover in the small intestine. And what we did here, we use a finite element to simulate the capsule, whether our capsule is sufficient, has sufficient power to cross over the circular fault. And we have also carried out the experiment on the small intestine and try to cross over the circular fault. And also in this case, we try to manipulate our capsule robots in a more complex intestine structure. And here we try to develop the finite element model and to understand the contact pressure between the small intestine and the capsule when it's vibrating, and we try to reduce the force generated on the intestine in order to mitigate the influence on the patient. And this is our ex vivo testing. We use a portion small intestine, and we put our capsule in a fully surrounded intestine in this case. So you can see we can drive that freely in the small intestine, and it is sufficient to progression in the small intestine. So so in my talk, initially I gave you the background and motivation of this research, and then I studied the working principle of our design. Then I introduced the mesoscale prototype. Initially, we start to think about how to understand the dynamics of the system, and we can figure out the best parameters for control. And then by using the experience from this mesoscale prototype, we further developed this standard-sized prototype, which is 26 millimeter in length and 11 millimeter in diameter. So our future work will focus on this system optimization and integration, and we are aiming for this in vivo test using animals. So this is the team members who have involved in this research work, and the acknowledgement, the funding supporting this research. Finally, thank you very much for your attention, and I'm happy to take any questions.